Thank you for tuning into the Science Channel. Today I'm joined with my colleague Tranja, and we'll be discussing Ronald J. Gillespie.
Well, I guess the first question you're wondering is who Ronald Gillespie is.
Dr. Ronald is a well-known chemist who was born on August 21st, 1924 in London, England.
He was born into a poor family. However, he overcame his financial burdens. Ronald prospered in academics, especially in sciences.
Ronald's education consisted of a bachelor's, master's, and doctoral degree from the University of London. In the late 1940s, he pursued an assistant lecturer career and was promoted to a lecturer.
Later down the road, Ronald became a professor at McMaster University of Hamilton.
He is currently semi-retired, however Ronald is actively conducting research.
Amongst his discoveries, Ronald was awarded with numerous awards for his outstanding accomplishments.
Some of which include Fellow of the Royal Society, Torrey Medial, and McMaster Student Union Award.
In addition, he also investigated non-aqueous acidic solvents, where he discovered the highest known acidity called superacids.
Superacids have a more acidic pH compared to 100% sulfuric acid, thus allowing them to react with hydrocarbons, and they are the primary catalyst in the chemical industry.
His most significant research with Roland Nylam developed valence shell electron pair repulsion theory, also known as the VSEPR theory.
You must be wondering what the VSEPR theory is and its significance.
The VSEPR theory is basically a set of rules that helps us determine the geometric shape of a molecule based on the central atom. VSEPR theory aims to reduce repulsion between electrons. Due to their like charges, the electrons spread as far apart from each other as possible.
It's important to note that repulsion can occur between electrons that are unbonded and bonded in a molecular or polyatomic ion.
VSEPR can determine the shape and the polarity. In each molecule and polyatomic ion, there are a bonding pair of electrons. The electrons shared between the central atom and the atoms which it's bonded to are referred as the bonding pairs, whereas the non-bonding pairs are the electrons that are not shared with another atom, also referred to as a lone pair.
Lone pair of electrons will consume more space than bonded pair of electrons. The non-bonded pairs are spread over a large volume of space, allowing them to repel bonding electrons. As a result, it's best to replace the bonded pair of electrons as far apart from the lone pair to reduce repulsion.
There are multiple bonds that can be formed, single, double, or triple, based on the available electrons. However, regardless of what type of bond they are still considered one VSEPR pair. You must be wondering why this is the case. It is to create an idealized geometry because multiple bonds would have influenced distortions in the ideal geometry similar to lone pairs.
Furthermore, a double bond consumes more space than a single bond. This is because double bonds have a higher electron density compared to a single bond. The higher density allows the atoms to take up more space than the atoms in a single bond.
When discussing the VSEPR theory, a common notation is used to describe the shape of the molecule. A represents the central atom of the molecule, X represents the atoms attached to the central molecule. Lastly, E signifies the non-bonding electron pairs.
For instance, methane through the AXE system is known as AX4, where carbon is the central atom surrounded by 4 hydrogens. However, some molecules have lone pairs. For instance, water is noted as AX2E2, one central atom being oxygen, 2 attached atoms, the 2 hydrogens, and 2 lone pairs of electrons on the oxygen.
While drawing 3D molecules, keep these rules in mind. Draw the Lewis structure first and only focus on the central atom and electron pairs. Count the total VSEPR pairs, make sure to pay attention to any charges. Then predict the shape based on the electron group and lone pairs.
Let's go into some detail here. The goal of VSEPR theory is to minimize the amount of electron pair repulsion around the central atom of the compound. This is because the VSEPR theory is based on one idea, that the geometric shape of the molecule is mainly given by the repulsion between the electron pairs around the central atom.
Electrons minimize their repulsion when they maximize their distance. Keeping this idea in mind, we are able to determine the molecular shape as it allows the electron to be located in a specific spot. This allows us to predict the shape of the molecules such as tetrahedral and trigonal molecules, which the valence bond theory and hybridization were not able to explain.
The number of electrons can be counted by adding the number of bonded atoms plus the number of lone pair of electrons. When the counting is done, 3D distribution is predicted by arranging all pairs of electrons as far apart as possible. This also gives you the level of hybridization.
I guess the next question would be, how do you determine the shape of molecules? We first draw a Lewis diagram of the molecule and include all the valence electrons around the central atom. We count the electron pairs around the central atom and determine the geometric shape of the molecule based on the chart provided.
Created using Powtoon.